Hello students, we will discuss IB Physics SL Paper 2, May 2019, Time Zone 2. In this paper you can use calculator. My name is Nariman Nalim. I am located in Baku and here you can see my mobile and email. To prepare for exams, the main huge textbook is of Oxford 2014 and short textbook is by Tim Kirk of Oxford 2014. From examiners recommended to have guide, but for sure you should have physics data booklet, first assessment 2016 copy. Why this booklet is important? Because it has formulas and this booklet is available for you at the exam, so you can look for formulas during exam. This is the cover page. Question 1. A student strikes a tennis ball that is initially at rest so that it leaves the racket at a speed of 64 meters per second. The ball has a mass and the contact between the ball and the racket lasts for 25 milliseconds. A. Calculate I. Average force exerted by the racket on the ball. So given is initial condition u equals 0 meters per second, v equals 64 meters per second, mass, so here mass, is given, and so mass should be small. And time, we convert milliseconds into seconds. So section 2.4 of booklet give us the following formulas. Momentum equals mass times velocity. Force equals change of momentum divided by time, which is mv minus mu divided by delta t. Putting the known values, substituting the known values, we get the force to two significant figures. It will be 150 newtons per second. Double I. Average power delivered to the ball during the impact. So section 2.3 give us a formula for kinetic energy. Note in the booklet definition of power. It is energy transferred divided by time taken for transfer. Because energy transferred is kinetic energy, we divide kinetic energy by time, substitute the given values, and we get 4.8 kilowatts to two significant figures. B. The student strikes the tennis ball at point P. The tennis ball is initially directed at an angle 7 degrees to horizontal. The following data are available, so these data are also shown on the picture. Calculate the time it takes for the tennis ball to reach the net. So we should resolve velocity 64 meters into horizontal component and into vertical component. Horizontal component will not change, so it will move horizontally at constant speed. So constant speed motion to the right so the value of horizontal component is 64 cosine 7 degrees. Distance 11.9, so velocity equals distance divided by time, time equals distance by velocity, substitute the values, you get 0.187 seconds. Shows that the tennis ball passes over the net. Actually, what they ask is the height when the ball passes the net. Let's choose the positive direction upwards, then coordinate of the height will be 2.80 initial position plus displacement. Time we know, u equals, so initial velocity will be from resolution minus 64 sine 7 degrees, and acceleration is downward 981, so downward means negative. And initial velocity is also downward. This is also why it is negative. So constant acceleration downwards, we need section 2.1, displacement, formula without V. We choose formula without V, substitute values, and we get displacement will be minus 163. It means that coordinate at this time will be 280 minus 163, 117 or 1.2 to the two significant figures. So the height that it passes above the net at 0.910. So 1.2 is greater than 0.91. So passes over. This is a bit tricky question. Determine the speed of the tennis ball as it strikes the ground. Although they ask speed, we should find the velocity. They don't ask about horizontal component or vertical component. They ask about total speed. So conservation of energy tells us that change of kinetic energy equals change of potential energy by absolute values. Change of kinetic energy is half mv squared minus half mu squared. Potential energy decreases from height capital H to 0, so mgh. Rewriting this formula, making square root, we get 64.4. C. The student models the bounce of the tennis ball to predict the angle at which the ball leaves a surface of clay and surface of grass. The model assumes during contact with surface the ball slides. The sliding time is the same for both surfaces. The sliding frictional force is greater for clay than grass. The normal reaction force is the same for both surfaces. Predict for the student's model without calculations whether theta will be for a clay surface or for greater for clay surface or for grass surface. So here we have the following information. Normal force is the same, so vertical component of velocity is the same. During contact, frictional force will decrease horizontal component, but not vertical component. Horizontal component will decrease more for clay, as they say, because frictional force is greater, hence angle is greater. So horizontal component for clay will be less and angle will be greater. For grass, for example, here smaller angle. Question 2. A container of volume is filled with helium gas of pressure and temperature. Assume that this sample of helium gas behaves as an ideal gas. A. Molar mass of helium is 4 grams per mole. Shows that the mass of helium atom is 6.6. So molar mass equals Avogadro number by mass of helium atom. Rewriting this formula for mass of helium, we get 6.6 approximately to two significant figures, 10 minus 27 kilograms. Estimate the average speed of helium atoms in the container. Section 3.2, kinetic energy of a particle. And kinetic energy, on the other hand, is half mv squared. So half mv squared equals this expression, K Boltzmann constant Kb. So all values we know, and rewrite for V square root, and we find that speed is very high, 1.4 times 10 to the third meters per second, to two significant figures. C. Shows that the number of helium atoms in the container is about 4 times 10 to the 20. So section 3.2 give us number of moles. So rewriting for number of moles and understanding that number of moles is number of atoms divided by Avogadro number, rewriting this formula for N, substituting known values, we get 3.7 times 10 to the 20, which is approximately 4 times 10 to the 20. D. A helium atom has a volume so much. Calculate the ratio total volume of helium atoms, volume of helium gas. Volume of helium atoms will be number of atoms by volume. So we multiply, we get the value, and then we find the ratio. So the ratio is very small, 5.6, 10 minus 5. Double I. Explain using answer to DI and with this reference to kinetic model why this sample of helium can be assumed to be an ideal gas. For an ideal gas, particles are assumed to be point objects, so very small size. Result in CI shows that volume of helium atoms is negligible compared to volume of helium gas. Hence, assumption is justified. Question 3. The diagram shows the direction of the sound wave traveling in a metal sheet. So it travels in metal sheet and here goes closer to normal because for sound speed in metal is greater than in air, opposite to light. Particle P in metal sheet performs simple harmonic oscillation. When the displacement of P is 3.2 micrometer, the magnitude of that oscillation is 7.9. Calculate the magnitude of acceleration of P when its displacement is 2.3. Section 9.1 give us relation between acceleration and displacement. We see that acceleration is proportional to displacement, and ratio of acceleration to displacement is constant, actually equals omega squared. So we have one moment x1 a1 and second moment x2 a2. Substitute this into the expression, rewrite for a2 and get 5.7 meter per second squared. The wave is incident at point Q on the metal ear boundary. The wave makes an angle of 54 degrees with a normal at Q. The speed of sound in metal is 6010 meters per second, and the speed of sound in air is 340 meters per second. Calculate the angle between the normal and the at Q and the direction of the wave in air. So we have Snell's law, section 4.4 of the booklet. Rewrite this for second media sine theta 2 and then find inverse function sine minus 1 of this expression. We get 2.6 degrees. The frequency of sound wave in metal is 250 Hz. State the frequency of wave in air. The same, 250 Hz. Determine the wavelength of the wave in the air. Frequency doesn't change, so frequency is 250. Section 4.2 give us wave equation. Speed equals frequency by wavelength. So wavelength will be speed by frequency. Substituting values, we get to two significant figures, 1.4. D. The sound wave in air in C enters a pipe that is open at both ends. The diagram shows the displacement at a particular time t of the standing wave that is set up in the pipe. On the diagram at time t, label with letter C a point in the pipe that is at the center of the compression. So because I have drawn this red line and all particles on the left are approaching this line because they have positive displacement to the right. All particles on the right are approaching this line, so as a result in here we are getting compression. So actually it is a line. Now we come to question 4. Light bulbs X, Y and Z each of resistance 4 ohm, are connected to a cell of EMF 12 volt. The cell has negligible internal resistance. A. The switch is initially open. Calculate the total power dissipated in the circuit. When the switch is open, we can forget about this part because no current flows here. And we have YZ connected in series to cell. Potential difference across Y and Z will be equal to EMF 12 volt. And we can consider this section as a section with some total resistance. From section 5.2, we choose formula for power in which we have only voltage and resistance. Voltage, as I said, is 12 volt. Total resistance for two resistors connected in series is the sum, 8 ohm. We substitute values and we get 18 watt. The switch is now closed. State without calculations why the current in the cell will increase. So when we close the switch, current through Y and Z will be the same, but additional current will flow through X, and total current through battery will increase. Or we can say that we connect X in parallel to Y and Z, decreasing total resistance, so power will be increased. So let's see what we have in the mark scheme. A resistor is now connected in parallel, reducing the total resistance. Current through YZ unchanged, and additional current flows through X. Deduce the ratio power dissipated in Y with S open and with S closed. If we look to the formula, this formula depends only on voltage, which is 12 volt, and resistance, which is 8 ohm. Nothing changed, so ratio will be 1. Question 5. The proton moves along a circular path in a region of uniform magnetic field. The magnetic field is directed into the lane of the page. Label with arrows on the diagram the magnetic force on the proton, I. So because we have circular motion, for circular motion always force is towards the center, so this is why I have this arrow to the center, and this is force. I, velocity v of the proton. Here we have question. First of all, velocity is along tangent, but we don't know clockwise or anti-clockwise. Let's use Fleming's left-hand rule. So fold all fingers, point the first finger, which is filled, into the page, turn your palm anti-clockwise, and open thumb to show a long F. Then open second finger, it will show you anti-clockwise motion. So your second finger will show you, just a moment, just a moment, okay, right, so second finger will show tangent, and we will label it V. So this is velocity. B. The speed of the proton is so much, magnetic field strength so much. For this proton magnetic field strength. For this proton, determine in meters the radius of the circular path. Give your answer to an appropriate number of significant figures. Section 5.4 of the booklet give us formula for magnetic force acting on charge moving with some velocity in magnetic field at angle theta. Angle is 90 degrees, so we have force equals QVB. On the other hand, we have circular motion, and for circular motion, force equals mv squared over r. This force is the same expressed in different terms, so we rewrite these expressions, rewrite for QBV, then for R, substitute masses. So mass of proton we look for in the booklet. The charge of proton equals charge of electron, also we look it in the booklet, and we get to two significant figures, 0.54 meters. Next question is 6. Deuterium undergoes fusion according to the following reaction. So we have deuterium, and deuterium give us tritium plus some particle. Identify particle X. So if we write this equation with unknown A and B, so we should balance top values and bottom values. Top values balancing give us 2 plus 2 equals 3 plus A, so A equals 1. Bottom values balance give us 1 plus 1 equals 1 plus B, so B equals 1. So this particle has 1 and 1, so 1 means that it is hydrogen, and 1 actually it is proton. So it is isolated proton. The following data are available: B, for binding energies per nucleus for deuterium, for tritium. Right. Determine in mega electron volts the energy released. So we have 2 nucleons here in one deuterium, energy per nucleon, 3 nucleons for tritium, and energy for nucleons. Isolated proton has no binding energy. So for isolated proton, binding energy equals 0. So energy before equals E1, energy after equals E2, plus change. E1 equals 2 deuterium atoms in each 2 nucleons by energy of nucleon equals 448. Energy of tritium, 3 nucleons, energy per nucleon 834. Difference 386 mega electron volts. So much energy is released. I remind you the binding energy is negative. This is why increase by absolute value actually means decrease. Suggest why for fusion reaction above to take part, the temperature of deuterium must be very high. The deuterium nuclei are positively charged and repel. High temperature and hence high kinetic energy of deuterium are required to be able to overcome electric repulsion. C. Particle Y is produced in the collision of a proton with cation minus in the following reaction. Cation minus plus proton turns into cation 0 plus cation plus Y. The quark content of some of the particles involved are the following. Identify for particle Y the charge. Charges from the booklet, charges of quarks from the booklet. So composition, K plus is antiparticle of K minus, so this is why it is up quark and anti-strange quark. Now charges, left side. For quark minus, cation minus, we get minus 2/3 minus 1/3, which is minus 1. Actually, this minus tells us the charge of cation. Minus 1 plus 1 for proton give us 0. So initial charge is 0. Right side. Now we work with cation 0, so we see the charge is 0. Cation plus antiparticle charges plus and Y. So the charge should be equal to 0. It means the charge of Y equals minus 1. In terms of charge of electron, it is minus charge of electron. Now strangeness. From booklet, section 7.3, strangeness of S particle is minus 1. Anti-S, 1. It means that cation has strangeness minus 1. Cation plus strangeness plus 1. And cation 0, strangeness plus 1. So left side for strangeness. Cation minus 1 plus 0 equals minus. So initial strangeness is minus 1. Right side. Cation 0 plus 1, chiron plus 1, plus y should give us strangeness minus 1. It means the strangeness of y is minus 3. Question 7. The average temperature of ocean surface water is 289 Kelvin. Oceans behave as black bodies. A shows that the intensity radiated by the ocean is about 400 watt per meter squared. Section 8.2 gives us the power radiated by object with temperature capital T. For rewriting this formula for intensity, what they want, intensity is power by area. Recalling that for black body emissivity is 1, sigma is constant, Stefan-Boltzmann constant, and substituting the rest values, we get rounded to one significant figures, 400 watt per meter squared. Explain why some of this radiation is returned to the ocean from the atmosphere. 3 points from Mach scheme. Most of the radiation emitted by the ocean is in the infrared. This radiation is absorbed by greenhouse gases in the atmosphere. The gases re-radiate partly back towards the ocean. This finishes the paper. I can tell you that this paper questions are 95% exactly the same as in HL paper. Of course, in HL paper you have more topics and more questions. Thank you for your attention.